Hey everybody, how's it going? Good, great, that's awesome. I'm glad to hear the front row is feeling good. I know it's after the break, but yeah, I'm going to talk a little bit today about how Instagram.com works, which is the web experience for Instagram. First, a little bit about myself, and then I'll stop talking about myself. I swear I'll make it short. My name's Pete Hunt. I work at Facebook, and I manage the Instagram.com web team. So we're mostly like a JavaScript, CSS, a little bit of Python team. And we build everything that you see on the web for Instagram.com. That includes some things that you do see, some things that you don't see, and some web views inside of our mobile app as well. Before that, I was working on our photos and videos team at Facebook, doing a variety of front-end and back-end things. And I'm also kind of part-time on our product infrastructure team, working on projects like React, which is our JavaScript framework. So Instagram.com. Seems like a lot of people have been to Instagram.com. It's a single-page application rendered entirely in JavaScript using React, which is our library. And it's built by a really small team. So the first iteration of it was built about 2 years ago by me and a designer. And since then, we have grown to the enormous size of 4 engineers, which is very small by Facebook standards. And our scale is pretty large, too. So if you've been to Instagram.com before, you've probably seen a user profile, including a really hilarious video of my roommate in the upper right-hand corner. And you've seen, user profile, photo pages, maybe a feed if you've logged in of all of the photos of people that you're following have posted. But you probably don't see a lot of the work that we do. We do a lot of internal tools. We also do a lot of tools for big brands that really want to understand their Instagram account and their ad performance and stuff like that. So we do a lot of high-performance data visualization that involves downloading lots of data onto the client efficiently and rendering, data visualizations and UIs in Canvas and SVG, again, all powered by React. But Instagram is most well known as a native app product. So why do we even build things on the web in the first place? Is it because we get a better user experience by building with the DOM and JavaScript and CSS? If you've ever used a web app, you know that that's not true. Is it because of discoverability, because people can Google for your application and find it? I don't think so. Because the App Store has gotten to be a pretty good distribution mechanism for applications on your mobile devices and tablets. Instead, it's really all about getting your application onto the user's device or laptop on demand. They don't have to wait to download a 10 megabyte executable in order to run their code. It's run in a security sandbox, so you don't have to worry too much that it's going to do something malicious. You also get upgrades for free on demand. And we're starting to get there a little bit on the native mobile platforms with these beta channel type of experiences, but we're not quite there yet. So today I'm going to talk about single-page applications, if you've ever heard of them, why they're great, why they suck, and how we can mitigate the suckiness of single-page applications. Now, there's a number of different things that single-page applications do that suck. Static resources, data fetching and routing, they're different, and you have to figure out ways to do them efficiently and effectively. Search engine optimization and performance are other aspects. Those are probably 3 different talks. So I'm going to focus specifically on static resources. So how do we get the JavaScript, the CSS, images, web fonts, all of that great stuff onto the user's device as quick as possible? So let's look at how we've historically built on the web and how we're going to start moving to build today. So if you've ever built a traditional web application using something like Rails or PHP or Django, something like that, it generally works like this. When the user wants to perform an action, they either can generally click on a link or submit a form. And what that does is that sends an HTTP request to the server, and it gets back a full HTML page. And then the browser repaints the entire screen, scrolls up to the top, and there's a brief flash before it's ready to go. So the ability to build that application, or it's fairly easy to build applications in that way, right? When the data changes in your app, you simply hit the refresh button and you're always up to date. And building HTML from database queries is fairly well understood. The performance of loading an HTML page, it's okay. It could probably be faster. but it's not that bad given the user experience that you can give to the user. But the problem is that the kind of breadth of user experiences that you can build using this model is very narrow. So every single interaction, you have to go to the server and wait for a full page to be rendered and sent down. And that's just not a great user experience. So in the early 2000s, when Gmail started to get popular, we started to see the rise of what I like to call server-rendered AJAX. So the way that we have changed this previous model is we organize our page into small chunks called pagelets, which would be a separate section of the page. And when the user performs an action, we simply do an HTTP request to the server, we get back some HTML, but rather than the HTML for the full page, it's an HTML for a small part of that page, and then we stick it into a DOM node. So this is actually really fast because we don't have to go to the server and back and reload an entire page when only a small part of it has changed. The user experience is a little better than a server-rendered app because when you perform an action, only the part of the page that needs to change changes. So if you're typing into a text field somewhere else or you've scrolled down the page, you don't lose that state in the browser. The problem is it's actually very difficult to build complicated applications in this way. Because if you have two pagelets that rely on related data, it's very hard to keep those synchronized, if not impossible. So if we were building Facebook newsfeed and had each story as a pagelet, and we had a photo viewer that also relied on the same data, so there's a photo in the newsfeed and a photo in the photo viewer, if the like count on the photo changes, we'd have to figure out a way to synchronize both pagelets in the photo viewer and the newsfeed, which is a pretty hard thing to do because this is such a primitive technology. So the trendy way to build applications in 2014 is a single-page application. And this is fundamentally different from the way that we've built web applications in the past. When you load the web page, you're simply downloading a bunch of JavaScript. Often the HTML for your application is simply an empty body tag. When that application is downloaded, it renders the UI client-side. So it either generates markup client-side or manually creates DOM nodes in the browser and renders them for you. And when it needs to fetch data, it goes to the server and gets back JSON or XML or some other data format rather than HTML. So with a single-page application, it takes a while to download that JavaScript. It's fairly easy to build because you have control over the entire client experience. But it has the best user experience because you don't have to rely on logic on the server to respond to a user action. You can respond to it immediately and then wait for the server because it might be on some remote location over a crappy network. So when we were deciding how we were going to build our next products, we decided that user experience was most important for us. We had to build on the web because we wanted that great ability to deliver updates instantly. But we also wanted to make sure that that was balanced with as good of a user experience as we could create. So we went with a single-page app. Now, a really hand-wavy summary of the trade-offs is in this table, and I kind of just made this stuff up. But it has some truth to it. The load performance of single-page applications is generally pretty poor. I'm sure a lot of people here have ranted about, apps that take a long time to load in the browser. You simply stare at like a blank page until all this JavaScript finishes downloading, parsing, and executing, and then it finally pops up the UI. But we want to really get that great user experience once it's loaded. So how do we get a single-page app's load performance up to par? Well, we have to break it down into two primary criteria. We want to minimize the number of HTTP requests, and we also want to minimize the number of bytes downloaded. So every single HTTP request incurs a penalty because you have to go to the server over a noisy network and get a response over a noisy network. And you also want to minimize the number of bytes downloaded for obvious reasons as well. So anybody here built for the web before? Phew, okay, good. Never know at OSCON what people are using. How many people have heard that concatenating all of your JavaScript into one file is a best practice? All right. That was a risky one. I wasn't sure if people had heard that one. So downloading JavaScript the wrong way is concatenating all of your JavaScript into one giant file. So if we did that for Instagram, we would have a JavaScript file that's 9.5 megabytes. Now, a lot of times you report gzipped JavaScript size when you're talking about the number of bytes downloaded. So really, that's only going to be 2.5 megabytes over the wire. But first of all, 2.5 megabytes is still pretty big. And second of all, the web's strength is delivering applications on demand across a variety of devices. So you have to think about mobile when you're doing these things. And so we're still talking about parsing and evaluating 9.5 megabytes of JavaScript on a potentially resource-constrained device. And that's just a huge bummer. So there is a better way. Only download the JavaScript you need at a given point in time. So you have a single-page application. And remember, it's just one web page that loaded. It downloads a bunch of JavaScript. And then when you want to change virtual pages, like if you are on the Instagram newsfeed and you click on somebody's name, you go to their profile page. It's not a real page load because you're not going to the server and fetching new HTML and re-rendering. You're simply fetching the data needed, and the JavaScript on the client is re-rendering that UI. So rather than calling those two sections, the feed and the profile, pages, let's call them entry points instead. So Instagram.com has 17 entry points, just to give you an idea of the relative numbers here. So we really want two properties in our system. The first is that we only want to download the JavaScript that we need at a given point in time. So when you go to the profile, you don't want to have to download all of the JavaScript for the feed, because that's completely unnecessary. You might not even be going to the feed. And when you scale up to 17 entry points, that's effectively downloading 17 different applications just to use one. Additionally, you can navigate between these different entry points. And so when you navigate from the profile to the feed or the feed to the profile, for example, on Instagram, both of these use React, and we shouldn't have to download React for each entry point. We should be able to reuse the modules that we already created, parsed, and executed for the feed when we go to the profile. So how do we do this? Again, Instagram is a very, very small team trying to hit deadlines. So we don't have time to rebuild a bunch of unique infrastructure for this. So the first thing that we did is we adopted a module system. We went with CommonJS because I think it's got the most momentum and the best tooling today, but it doesn't really matter what module system you use, as long as it has a way of expressing dependencies between modules. So a lot of people, when they start writing JavaScript, they put it into multiple files, and they think about it in terms of files, and they drop script tags into their web page. When you build with modules, modules have a very fine-grained dependency graph. So I can say my profile entry point depends on both the photo modal and React, and we must load those before we can execute the profile entry point. Just like the feed entry point depends on both of those modules as well. And in this example, the photo modal also relies on React. So since we're building with modules and not flat files, we need a way to package these modules into flat files so the browser can execute them. Because the browser doesn't understand what a module is. It understands what a flat JavaScript file is. So we use a process called bundling modules for the browser. And you can think of this as a compilation step for JavaScript. Well-known tools that do this are Browserify and Require.js. And basically what they do is they take this dependency graph and they turn it into these flat files that you can just run in the browser natively. And the way that you generally express these arrows, these dependencies between modules, is by using a magic global function called require, which would be equivalent to the import statement in Python or another language. So this is great. We're able to take this dependency graph and take each module, make it into a file, and send it down to the client. But we really want to have a high-performing application. So we want to run an optimization step on our bundles. So I've highlighted each bundle in a different color here. And what our optimizer noticed is that our two entry points have a lot of app-specific code. So we shouldn't bundle the profile and the feed together, because just because you're looking at the profile doesn't mean that you need to go get the feed. But what our optimizer also noticed was that they both depend on photo modal and React. So we should bundle both of those into the same shared.js bundle, which we'll reuse for both entry points. Now remember, this is an optimization problem, so it's trying to minimize both the number of HTTP requests and the number of bytes downloaded. So this actually does add an unnecessary extra HTTP request, but it trades that HTTP request for less bytes downloaded as you navigate between applications. So this is a trade-off that your optimizer manages for you. So now that we have a way to build an optimal set of bundles, we need a way to actually load them onto the client. So another property of single-page applications is, again, when you click on a link, you're not actually going to the server and fetching a new web page. Your JavaScript application is interpreting that link and then deciding what to render. Now, the piece of code that interprets that link and that URL is called a router. And we put the client-side router on every single entry point. Now, if we were to build this naively, and you think about how this would be implemented, the router would have to express a dependency on every single entry point because it has to look at the URL and then render each of those entry points, depending on what URL it gets. That would result in one giant bundle, which is exactly what we want to avoid. Instead, we want a way to express what we like to call split points. So we can asynchronously load bundles on demand. So what this code is doing is, rather than calling a synchronous require, which is how you normally express dependencies in common JS modules, there's an asynchronous version. And what this says is, hey, module system, when we get the profile URL, try to go fetch the profile bundle. And when it's ready, I'm going to hide the loading indicator, and then I'm going to render the profile. And the same with the feed as well. And then if the user bounces from the profile to the feed and back to the profile, those modules will already be cached, and these will execute synchronously. Now, under the hood, this will use XML HTTP request to asynchronously load all the JavaScript files it needs. But all you're doing as an end user of this system is expressing, hey, this part is OK to load asynchronously. JavaScript isn't the only thing that we care about when we build apps. There's a lot of other stuff that we care about. So has anybody been kind of following the escalation of build tools in the JavaScript community? I think there's a ton of them. There's Gulp, Grunt, Broccoli is one of them. And they all basically take a bunch of files and they transform them and they might combine them in some way and then they emit output. So you might use it to process your CSS through a preprocessor like Less or Sass. Or maybe you want to write in CoffeeScript, which is a syntax extension for JavaScript. And you need to run that through a preprocessor before you can run it in the browser. But notice I was talking about files right there. Shouldn't we really be thinking of these in terms of modules? We can put these in the dependency graph. So just because something is CSS doesn't mean that it's not part of the dependency graph. So we're rendering a bunch of markup or DOM nodes in JavaScript, and we want those DOM nodes to be styled with CSS. So we have to make sure that that CSS style sheet is loaded before we actually render that UI to the page. So we want to be able to express a dependency between the profile entry point and the profile CSS. And if we treat these modules like any other JavaScript module, they can be optimized with the exact same tools and algorithms that we use to get an optimal kind of set of bundles for JavaScript as well, and asynchronous loading, etc. So again, using CommonJS as the example for how we would do this, we would just use the same old require function that we use for JavaScript modules. So if I want to make sure that Twitter Bootstrap is in the page, I just say, hey, require bootstrap.css. And what the module system will do is it'll say, hey, I'm not going to execute any of this code until we have a style tag in the document that points to bootstrap.css, and that's loaded. We can do similar things for images as well. We can have our require function return a URL that points to the image. And then our bundler can look at the image and do different things depending on what type of image it is. So if our image is small, maybe we want to inline that and use a base64 encoded data URI so we don't have to do an extra HTTP request. If the image is large, maybe we want to render the UI and wait for the image to load. So we can point to a regular URL on a CDN somewhere. Now, under the hood, what happens is the bundler will look at these file types and make a decision. It'll say, hey, this looks like a style sheet. I'm going to rewrite it, and instead of just bundling in a string of CSS, I'm going to rewrite it into a JavaScript string and a little bit of code that will insert it into the document as a style tag. And with the image, it'll upload the image to the right place, and it'll replace this with a simple module that exports a string, which is the URL to the image. So you can use it just like any other JavaScript module. And you don't have to just do this with CSS and images as well. You can use any sort of static asset type here. So why don't we just hook our CSS preprocessors like less or Sass directly into the module system? Because we want to run this sort of transform on these files anyway. We're transforming CSS into a reference to CSS in JavaScript. We may as well run the less preprocessor along with that step. Similarly, we could do it with compile to JS languages like CoffeeScript or like TypeScript. Why should we treat all of these assets as something that's different? Why can't we just all treat them as one unified JavaScript construct? So when we started doing this at Instagram, we deleted our grunt file. We don't use a build system at all anymore. We use just the module system to build all of our static assets and optimize them. Because again, it runs over a dependency graph that can be optimized, not flat files that are completely meaningless when you load them in the browser. We need those dependencies. So I hate CSS, and I'm going to go rant on it for a little bit. All of the problems that you have with CSS get 10 times worse when you start building single-page applications. So if you think about it, when you're using a single-page application, any entry point may be loaded in any order. Maybe all of your entry points get loaded. Because remember, we never refresh the page. We just download more bundles, and we execute them. And that means that any or all of your style sheets may be loaded at any time and in any order. So specificity wars, conflicting class names, and dead rules all become much more problematic because you have a lot less control over the order of your style sheets and which ones are loaded and which ones aren't. So my specific problem with CSS is selectors. I really don't like selectors. And here's one example of how they break down, specifically in a single-page app. So if we land on the feed, we want all images on the feed to be rounded by 5 pixels. So we set border radius 5 on our feed CSS. Then let's say we navigate from the feed to the profile. We click on the author's name. All the images on the profile, we want to be 1 pixel, rounded corners. But if we bounce back from the profile to the feed, because the profile CSS loaded last, all of the images on the page will still be rounded by 1 pixel, even though the feed is expecting a 5-pixel rounding. So the feed UI is going to be broken. Additionally, you can have conflicting class names, and that becomes a much bigger problem when you're loading all of these modules into one page, because CSS is one big, happy global namespace. Not so happy. So if we were to land on the feed, and the feed has one notion of what an avatar is, let's say it applies that border radius. But then if the profile has a different notion of what an avatar is, and the user navigates to the profile, all the feed rules still apply. So even though the profile was not expecting rounded corners on this avatar component, it still gets those rounded corners because the feed CSS is loaded. And if you have 2 separate teams working on these projects, you need to coordinate what the meaning of an avatar class really means. And that can be a pretty big pain. The other thing is that CSS is kind of a write-only language. You write all of these rules, and then it's very difficult for you to figure out when a rule is no longer used. And the reason for that is when you use a lot of the selector features, like the cascade, the C in CSS, these rules depend on the structure of the DOM as to whether they're actually executed or not. So you need to know every single possible configuration of HTML that you will ever render in order for you to know whether it's safe to delete this rule or not. That's not fun. So we have a set of opinionated guidelines on the Instagram team for how to write CSS that works well in a single-page app environment. These are kind of cribbed from the way that Facebook writes CSS, but there's a lot of great documentation out there from Yahoo, Nicole Sullivan, Nicholas Gallagher's Suit CSS. They all kind of follow these general guidelines. The first is unambiguous class names. Namespace them aggressively. So rather than having an avatar class name, IG user profile avatar. Nobody's going to accidentally type IG user profile avatar. The second thing is that in almost all cases, we forbid cascading, and we only allow a single class name per CSS rule. In that way, it's very easy for us to see when a rule is going to apply or be dead, because we can simply grep for that class name in our code base, and if it's there, that rule is going to be used. And if it's not there, the rule can't be used. And it doesn't matter what the runtime configuration of the DOM is. And finally, we try to avoid overriding as much as possible. So if we apply multiple class names to a single DOM node, we want them to be orthogonal. We don't want them to have the same style properties and rely on the order in which that CSS was loaded. So I've talked a lot about single-page applications. They provide the best user experience that you can provide on the web. But you have to do it right. Otherwise, you're going to have your user staring at a spinner and a blank white page for a long time. So at Instagram, we wanted all of these great features. But we had a small team and aggressive deadlines. And we had no time to build all of this infrastructure. Facebook has a lot of great infrastructure, but it's this big PHP behemoth, and we're like on Django and all these other open source technologies. So we started looking for a tool that would do all this for us in the open source community. So we looked at Browserify, and that's all about making one giant JavaScript file. So that's gone. We looked at Require.js, and it either loves to issue HTTP requests or loves to build giant files, and doesn't have a great notion of multiple entry points. So we tried it out, and it didn't really work for us. We looked at build tools, too. Grunt was great for running our tests, but doesn't know about the dependency graph. So we can't optimize it. And Gulp is like a better Grunt because it works on streams, so it performs better, but it still works on the idea of files, not modules in your dependency graph. So again, we can't optimize it. So that was a non-starter for us, too. But then I found this awesome tool called Webpack. Now, I just want to let you guys know that this is not a Facebook open source project. This is some random guy in Germany, and he's super smart. And when it comes to static resources anyway, Webpack is the only open source tool that we found that does it correctly. And we have had this in production for a long time at this point. So right around, I think, November, we had this old system based on a forked version of Require.js. And it performed pretty badly. And I had just brought on this guy on our team named Nick Thompson. He was fresh out of college. And his first project was like, make the photo pages faster. Because when you loaded a photo page from the Facebook corporate network, which has a pretty fast connection to our data centers, it took 250 milliseconds. Again, huge bummer. So instead, we brought in Webpack. And we kind of did the naive thing. We used Webpack in the simplest way we possibly could. And we brought that down to 120 milliseconds. And while it wasn't perfect, it's still a 52% performance improvement out of the box without even trying. I like to think of this as falling in the pit of success. We simply, changed our modules a little bit to work with Webpack's idea of CommonJS and that asynchronous syntax. And because it's architected so well, and architected around the idea of a dependency graph of modules rather than flat files or modules that must be combined into a single file, you get a lot of just emergent great performance properties out of it. And coming from the Facebook world, where we are pretty good at knowing about how performance impacts user engagement and user sentiment, first page load performance is hugely important. You really don't want to make your users sit and wait for stuff to load because they get very angry. So in order to figure out how Webpack worked, we had to decipher these pretty cryptic documentation pages. So we distilled all of our knowledge that we gained from this experience into this little how-to document. It's sitting in GitHub. We're going to accept pull requests. And we want to really make this a great resource for people that really just want to get stuff done, make their site faster. They don't care about the philosophy of modules and all that stuff. They just want to get this going. This is a cookbook, very pragmatic. So my Twitter handle is Floydophone, and that's all I have to say today. I'll take questions or whatever. Thank you. The question is, like, how are we converting our web audience to the mobile app?
Yeah, like how effective is the web app driving?
We generally use the web to play to its strengths, and we use mobile to play to its strengths. So, for example, if we're showing big power user data visualizations, you're going to probably be on a laptop or a tablet where the web does pretty well. So in that case, we wouldn't want to drive traffic to mobile. But in the case of you're landing on a mobile photo page, and your experience would probably be better in an app, we'll try to bounce you into that app. I don't have any public conversion numbers that I can share, mostly because I just don't know them off the top of my head. But yeah. Yeah.
So when you're working with the actual CSS files in your project, do you divide those up by the entry points in the application? I mean, I know you talked about namespacing, but are you separating them all then in the project?
So the question was, how are we organizing our CSS modules? I would say most of our CSS modules are around 50 lines of code. So the way that Instagram.com is built is it's one giant React component, and then with React, you're encouraged to build lots of smaller components that compose these bigger components. So for each component, we have a JavaScript file and we have a CSS file. And so we can have hundreds of CSS modules that the optimizer will take care of, optimizing into smaller chunks. But those are all namespaced by the name of the module. Yeah. The question was our approach to testing single-page apps. It really depends on the rest of your tech stack and the types of problems that you see. I'm a big advocate for looking at what are our quality problems and going for a testing strategy that works for that. So when we're in fast iteration mode, when we're building a product that we don't know if the designer is going to like it or not, or if the customer is going to like it, we actually just don't write tests because that slows us down. We're testing things that we're going to throw away. When we get to the end and we're starting to feel confident that this is a product that people actually want, we'll look at the class of bugs that we have. So about a year or two ago, we had some pretty gnarly CSS before we had adopted these really strict conventions. And so when they would load in different orders, we would lose rounding corners, or we would lose a border on something. And so we actually have an open source tool from Instagram called Huxley, which is all about screenshot testing. And we were we're just going to click on all the buttons in different orders and screenshot it and pixel compare and make sure that our CSS isn't messed up. Since we started kind of writing our CSS in a more disciplined way, that's been less of a problem for us. And shameless plug for React, we don't have a lot of UI bugs because it's just the best JavaScript library ever. So, but we do have a problem with our data schema changing between the back end and the front end. So we might realize that we need a new field and some JSON field and some JSON API that we're hitting, and they might refactor that a little bit, and our front end doesn't expect that. So we have an integration test that hits the latest version of master on the server and makes some assertions about what the shape of the JSON is. So the test runner that we use is it's a Facebook one. It's called Jest. It's based on Jasmine, which is a really popular JavaScript open source one. And then on the Django side, we just use the built-in Django test runner. Yeah.
So your module architecture on Instagram, do you guys bundle your CSS or HTML commercials into that? How does that work?
The question was, what do our how do we bundle our modules at Instagram?
Yes.
So we're a 100% React app, so we don't really have templates. We have JavaScript, and the JavaScript kind of contains templates, you can think of it that way, and CSS. So we have a number of different components in a component library. So for example, we would have a newsfeed component that is made up of newsfeed story components that's made up of photo components or image components. For each of those components, they have their own JS file, and each of those JS files requires a CSS file, or in our case, a Sass file that's right next to it in the directory structure. So you can inspect a component, look at the CSS classes, and say, oh, IG user avatar, I'm going to open up useravatar.js to change the behavior, or I'm going to open up useravatar.css to change the styling. Cool. Yeah. So the question was, do we use the JSX compiler at Instagram, and how does it fit into Webpack? JSX is an optional XML literal syntax for React, but it's a really good example of a compiled to JS language. Another one you could use would be like CoffeeScript or something. Webpack has the idea of loaders, which is similar to a browserify transform or a step in your make file like GCC or something like that. And it says, hey, when you require a file that ends in .jsx, run the JSX loader over that module, and it'll transpile it, and eventually you get down to vanilla JavaScript at the very end. And at that point, the optimizer kicks in. Now, the advantage of using a JSX loader in Webpack rather than doing it ahead of time is that when you're in development mode with Webpack, it knows only the files that have changed, and it only recompiles what it needs to. Whereas if you were using the traditional JSX transform, it'll recompile everything, and then if it notices a file changing, it'll change, but it doesn't know about the dependency graph. So if a lot of files are changing that you don't really reference, it doesn't know to ignore those. Yeah? The question was, how do we deploy these bundles when do we build the bundles and how do we deploy them? I really want to get to the point where we build them on demand and we cache them in a CDN. We're just not there yet because, again, we're a small team and we get to the point where it solves our problems and then we move on with other stuff. So the way that it works right now is in development, we basically we run this watcher command for Webpack and then it puts it into the Django static root. And then we just fetch the files from Django. When we go to production, our Djangos are configured to have a different static root URL, which points to CloudFront or one of these CDNs. And we upload our assets to S3 before we actually flip over that static URL. So we have different versions of static resources. So yesterday was V2, today is V3. So first we upload all of our assets to S3 in the V3 folder. And then once those are all successfully uploaded, we flip a bit in a database somewhere that says, OK, current static resources version is V3. And then we're pushed. So we can actually roll back in like 2 seconds.
Are the slides available?
Yeah, I can put them up. I'll put them on SlideShare. Floydophone on SlideShare. Yeah.
Do you have any recommendations for resources to learn more about CSS best practices? Because it seems like we learn a lot from learning.
Yeah. The question is, any other resources for learning CSS best practices? The Yahoo team has some good documentation on something that they call atomic CSS, which does a really good job of dealing with these types of issues. Yandex has something called bem.info, and they have a pretty good philosophy towards CSS. Nicole Sullivan's object-oriented CSS, Nicholas Gallagher's Suit CSS, those are both really good as well. Facebook kind of is the average of all of those, I would say. Yeah. The question was, what's our strategy around building more features in the web versus the mobile platform? Again, we're playing to the web's strengths. So it's pretty hard to beat a device in your pocket that has a camera on it when it comes to taking photos. Just like it's hard to beat, looking at data and really being a power user on a desktop. So features that make sense on kind of bigger screens and people sitting at desks, we'll build on the web. Features that make more sense when you're on the go on a mobile device, we'll generally build on mobile. The one exception is kind of the glue between applications. So like our photo pages, you'll be bounced into a photo page from Twitter or something like that. Taking advantage of the web's linkability, we'll generally use that as glue between native apps. Cool. Anything else? Great. Well, thanks, guys.